Hello. Happy Sunday. Welcome to the stream. Hope you're having a great Sunday. Folks in the U.S., I hope you had a lovely holiday. If you're not in the U.S., welcome as well. Today, we're going to be trying to finish Chapter 4 of Essentials of Compilation. We are doing Essentials of Compilation in Gleam. So if you are not familiar with the book or with the language, this might be a bit of a challenge for you, but we're pretty deep into this project. I didn't get an exact count, but we're at least like 15 episodes, which is quite a bit. But we've made really great progress into the book, even having to deal with the differences between Racket and Gleam. So I feel like we're doing pretty well, and we'll finish up Chapter 4. Chapter 4 is about Booleans and conditionals. So we added, in our previous chapters, we had just integers as our data types. Now we have Boolean values as data types, as well as conditional expressions. So you can do sort of like if then else type stuff, as well as having comparison operators, because comparison operators can take multiple types in some cases, but always return a Boolean. So we are about to finish that up, and I wanted to check in with the state of our tests, see if we didn't accomplish anything in our tests that we need to before we move on. And then we'll finish this out. There's actually not that many things to be adding. So let's have a look at where we are. Excuse me. Okay, so last time we finished this Uncover Live pass and the Build Interference pass. And we made a few changes to Build Interference. In that we have a new instruction, which is this move ZBQ, which is moves a byte register into a quad register, zeroing out the upper bits. So the most significant bits are zeroed. This lets us take a value out of the flags register in x86, which stores the results of comparison operations, and put that into a byte register, and then move the byte register into a quad word register. So that's what move ZBQ does, and that guarantees that if the comparison was true, so if two things are equal, then it'll be 1 in the flags. And so when you use the set instruction, pull it out of flags into, say, AL, which is a 1 byte register on this architecture, then you can use this move ZBQ to go from AL to, I don't know, a memory location or a register, and make sure that comes out as 1, and it doesn't get any like uninitialized data in there, and it also doesn't get filled with ones. So there, that's what this move ZBQ instruction does. We had to handle it specially using rule 1 of the interference. So this is a special case for move instructions, basically. And in this case, we treated the byte register as a projection of the quad word register. So this is saying we're treating AL, if that's the argument, as the least significant byte of a 64-bit register or an 8-byte register. So that means that it overlaps with that register. And so that's what we're using for this particular instruction. This means that they may be in conflict with one another. We'll see. So let's look at we've finished the test. So we added a test for assigning Boolean variables, and I think we had a test for branching. So this phase, build interference, is about building a graph of all of the variables, essentially, or all the memory locations that have to be live at the same time, and uncovering which ones basically can't be assigned to the same spot, right? So then that is used in the next phase, which is allocate registers, to walk the graph and then translate all. So it walks the graph, it extracts all the assignments for the individual variables and so forth, and gives them registers or stack locations. So then from this set of assignments, we can determine all of the registers that are used in the calling convention, and then also how many variables is spilled onto the stack. So if we ever get any derefs here, then we're just basically gonna find the we're gonna find the number of stack variables. So excuse me. And then we go through each of the statements in the program, each of the instructions in the program, and then substitute the assignments of all the variables with their actual locations. So for example, like you can see here in the add queue instruction, it's like, if you've got location A and location B, then substitute whatever A references to with an actual register or an actual stack location. Of course, if it's a literal, then you don't have to. I say a literal. If it's an immediate value, you don't have to substitute it. So I think that what I would like to do here is make one test for allocate registers, and then we'll go forward in the book and finish up with patch instructions. So that's what I'd like to do today, and then we might look at the challenge. The challenge is really interesting, but it might rely on some things that we don't necessarily have access to, things like global state. So we'll see about that. But let's make a test that maybe we can take advantage of one of these tests that we built here. And does this have variables? This one has one variable. I'd like something a little bit more interesting with branching. Let's look at explicate control and see if it has some stuff with branching that are interesting. Yeah, this has only one. No, let's see. This has two variables. Right, and this is also passing through the other phases. Now we could do something like create this kind of program and pass it through all the phases that come before, and then the problem is that we don't necessarily know what the instructions are going to be. So it might be better to come up with branching test. Let's just call it that. I don't know what we're going to do here yet, but let's come up with a pseudocode program, perhaps. And let's say A is read, and let's say if A is greater than 10, then B is read. If B less than A, then 1 else 2. Again, this is pseudocode. Okay, so then we need an else for this one. If A is greater than 10, we need to assign some more variables here. Let's say C is read, and D is read, and then we do C plus D. Okay, so that's our program. All right, so let's write this out real quick. So we're going to have a bunch of blocks. This might be too ambitious here. So we're going to have start. Actually, let's do it like this is going to be a list of instructions, and then this will be a block. 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 So let's do we'll call it A then. A else. Oops. And then we have B then. B else. Okay, so we're just going to construct this by hand. It's going to be a little bit painful, but yeah, so we can use var if here. So start is going to be call Q. Oh, not int call Q. Let's do call Q. Read int 0. Okay, and then there's going to be a move Q from RAX into var A. Is that not right? Oh, that needs an arg, not location. Register. Register var. Okay. And then there's going to be comp Q of, yeah, we need that from here. Var A immediate of 10, right? And then we have because this is a branch, we're not assigning this comparison to any variable. We can use jump if. Let's import that. We need CC. Oops. Let's do less than. Oh, what are those types? L LE, okay. LG. Okay, did we import jump if? We did. Okay. So jump if, and what does our program say? It says greater than, so we need G, and we're going to jump to block 1. These are not necessarily the block names that would be assigned by our algorithm, but they're close enough. And then the other one is a conditional jump, or unconditional jump to block 2. So this will be block 2. Now, why don't I name these? Since we don't care about the naming of the labels, let's call this A then, and A else. Okay. Yeah, it's just complaining it's not used. So then A then does another call Q, read int 0 arity, and moves register rex into var b. Okay, and then it does comp q, var a, var b, except I have that reversed. No. So the interesting thing about comp q is that the comparison is reversed. So I actually need to fix this one. It doesn't matter for the case, for this purposes of our example, but for correctness, I don't want to come back to this and go, wait, why are those reversed? So the left argument goes on the right in comp q. Thanks, Intel. Not confusing at all. All right, so if b is less than a, so we need to jump if less than, we'll go to b then, and otherwise unconditional jump to b else. Okay, so these are two leaf nodes which end the program, and this is a leaf node that ends the program. So all of these are going to end with jump to conclusion because they're in tail position. That's what they call that yeah. Okay. So for A else, let's skip over that. Let's do B then and B else because those are shorter. So this would be move Q immediate of 1, register rex, and then jump to conclusion. And here move Q immediate, do we say 2? Yeah. 2, register rex, jump to conclusion. Okay. And I would prefer you keep those on multiple lines, but whatever. Okay, and so for A else, we need to do several calls to read. Move Q, register rex into RC. And then we do another one, read int 0, move Q, register rex into var d. Why am I using rex here? Rex is always the return value of a call. Note that's essentially what we're doing at the end of these. We're moving our result into rex, even though we're not actually being called by anything. Okay, and then we do add q, var c, var d. So that's going to put the result in D. And then finally we need to is that what we would generate? move Q var D, I guess it's okay, into register REX. Okay. We did this crazy program. It doesn't make any sense. But we can know some things about this before we write out the rest of this. We know that ultimately D gets moved into REX, so D can be assigned REX. Those occupied the same logical position. That means that var C cannot be REX. It'll probably end up being like RCX or something like that. And in these others, A cannot be REX because we have to read into B. But B is not in conflict with C or D, so B could be REX. And then, after this comparison, it's no longer live. So there's no reason why. So we might what might happen is A and C both get assigned RCX, and B and D get assigned REX. That's my guess. But let's go ahead and make the program here. Okay, so we're gonna make x86. Well, what do we call it? We didn't import it as anything. Let's call it x86 program. Okay, so we need to actually use the things that we added here, new program. This takes body is a dict from list. Start. We have A then. A else is A else. B then is B then. B else is B else. And I don't think there's any other. Right. Okay, what did I do wrong? Oh, I need another paren there. Okay, what's wrong here? All right, so I need to construct these into blocks. Let base, let's say let block. Okay, and we already imported blocks, so we can spread that. And I'm just going to copy this to, oops, need another paren there. I'm going to copy this and duplicate. Except this needs to say body. So let's get our copying correct there. All right. So there's our program. And now that we have this program, we're going to pass it through going to pass it through uncover live. We're going to pass it through build interference. And then we're going to pass it through allocate registers. Okay, so that's going to be, this is going to be a flattened program. No variables remain. Only registers, stack locations, and so forth. So what we want to do is let's get the start block. We're going to do dict.get start, right? Okay, so this is a compiled block. There's only the body, right? So honestly, we can do let's say start body. So since we have multiple blocks here, this sort of comparison is going to be a little bit harder. So now let's basically do this. We are going to, I want to see if the instructions were translated in the way, or the assignments were given in a way that I expected. So we're going to do why don't we do A, right? We're going to do that. So we're going to use a spread there. Body is a list of instructions, but it's not letting me match on that. Okay, well let's just say this is start body. Okay, now it's just complaining it didn't move. I think it's just that it can't decompose at that level for whatever reason. I don't see why that would be a problem in Erlang. But maybe in JavaScript you can't match that, so that's why Gleam doesn't allow it. Okay, so now we're going to say move Q into A should equal, and this is an int instruction, so we're going to say int move Q. This is register RAX. And honestly, this is what I expect. Or not REX, RAX. So basically I'm saying here that I think that A is going to be assigned the register REX. Let's find out if we're right. Okay, it failed. Okay, so it gave A RCX, which I guess makes sense because I just contradicted myself. Remember I said that B needs to be RAX. Yeah, so okay, so then we should also check the next instruction. Comp Q A. Okay. comp q a should equal. I am doing this a bit of the hard way. Okay. And then there's no other variables to substitute in that block. You know, I think I want to back out this strategy. And what I'm going to do is I'm going to copy all of these. Well, there's no variables there, so we just need these 3 blocks. So we're going to say expected. And this is going to be int. We're going to replace these with all of the compiled version. So we said, again, in our assertion, this should be RCX. And so in this place, this should be RCX as well. Okay, and expected. Okay, so in the then, var b gets assigned rex, we believe. We will find out in a minute. And then we compare. So A was given RCX, and B was given RAX. And then we need to put those in the right language. And here I suggested that variable C should be given RCX. And D would be given RAX. So that actually means we have a no-op move here, similar to what happened in the previous block. And then you have int reg RCX. And we'll have another no-op move. Luckily, the patch instructions will eliminate those no-op moves, so we don't have to worry about that. Okay, so this is what we expect. Okay, so let's do start body should equal start expected. And then we'll do something similar for each of these other blocks. So we'll do a then body. And we do a then body should equal a then expected. And once more with feeling, we do a else body, and this is a else expected. And we'll find out how wrong we are in just a moment. A else body should equal a else expected. Okay, so we got a failure here. So we are on. So this is readint, jumping to B then and B else. Okay, so I expected B to be assigned REX, but it did not get assigned REX. It got assigned RDX. That's probably okay. I mean, it's fine. Actually, there's nothing wrong with that. The question is why. And I think it might be that well, the mysteries of the graph algorithm. I think, yeah, it's gonna make D not be in REX as well. Okay, so we got RCX, readint. Yeah, it put D in RDX. So the interesting thing about that is that we kind of have unnecessary, like this could be optimized. It may just be that the set of conflicts we build don't indicate that they can coexist. And that's interesting. I wonder if we have. So the thing is, allocate registers discards the conflict information. We're going to throw that in there. It's not going to be that helpful. Debug doesn't pretty print. I mean, it prints the values, but it doesn't print them nested. What I was thinking about is like what's the graph look like, and maybe we can't really inspect that with the IODebug. It's too complicated. That's okay though. I have good confidence in this. We can tell that it generates valid code. Like it's not assigning things that are in conflict with one another or that like might overlap. We're not losing any data. We're not causing any anomalies here. So I think that this is fine. I'm not especially happy that my assumptions didn't match up, but that's okay. Let's say add tests for allocate registers with one of the things that may be causing this discrepancy from what we expect is that we don't need that. Is that we're doing register allocation across this entire block, this entire program essentially. Because of branching, we have to take into account the entire thing, but there are cases where I guess like we have some things where C gets assigned RCX, but A was also RCX. It's just that A doesn't live long enough. So I feel like this is fine. The only one I was thinking might be interesting is that B could be assigned REX because REX is not in conflict with it. Like B dies before you get to the two branches that follow this comparison. The other thing is that D doesn't need to live separately from REX because ultimately the combination of adding those two together and then moving it into there means that it could occupy the same spot. In which case you'd have a no-op instruction here that could be removed by patch instructions. So it's fine. I'm not going to worry too much about it. Okay, so we are at the last section before the challenge. We may or may not do the challenge today, but we're going to look at patch instructions. We need to handle these two new instructions that we've added. So, first of all, we need to change this into x86 if. In which case, we've got okay, so all right, so we're going to do, we need to do let body is this. We need to adjust this because we didn't change any of the other fields, but we're patching instructions in the blocks. All right, and now oops, by the way, here's the repo if you're following along at home. Didn't mean to flip to that. So we need to handle comp Q and move ZBQ. And I'm going to collapse this down a bit so we can see both side by side. Okay, so we already handled move Q. Let's add so comp Q, the second argument of comp Q must not be an immediate value. So if this is an immediate as B, then we need to add a move Q of B into REX, and then we do comp Q of A and REX. Right, so they're saying, if you're comparing two immediates, you can eliminate that. You can eliminate that in the in a partial evaluator, but we didn't do that. So, okay. So the second argument of move ZBQ must be a register. Okay. So if we have so I think that what we do is say if this is a register as B, then we just We don't have to do anything. Instruction. Then we just return instruction. So if it's a register, it's fine. If we have anything else, the thing is, if it's not a register, the only thing it could be is a stack location. We should not be ever generating a moveZBQ that goes into an immediate. That doesn't make sense. So honestly, probably what we need to do is, rather than this, we're going to panic as invalid moveZBQ instruction. You know, I'm not a big fan of panicking, but like, because we have this enumeration, an argument can be either immediate, a register, or a deref, then like it makes sense to panic here. This means we have a bug in our code generation. I don't think we'll ever hit that, but it's important. It's important to handle that. Okay, so here, if we have a deref, what we want to do is generate a moveZBQ of A into register rex, and then honestly, I think we'll probably just be generating rex all the time. And then we want to move, not moveZBQ, but move q rex into B. So we have to introduce another move because this instruction requires a register as a second argument. Okay, so let's look at the patch instructions test. Of course, this is going to be wrong because we're using x86 if here. And okay, we should look at these figures in a minute. Okay, so this includes the prelude and conclusion, the prelude being main. This whole section they're talking about doing lazy evaluation of, or lazy generation of blocks. So we don't need to do that right now. Right, so this is kind of saying this is what happens if you delay generation of a block. and then trying to merge blocks by removing unnecessary jumps. So like if there's an unconditional jump and if you've eliminated a branch, then you can just combine those blocks. You don't have to jump. So this is all about optimization. Yeah, I think the main thing I wanted to look at here was this, right? And this. I don't know where they're getting their numbers. That's all right. Right, so this is the code with the registers assigned from here, and then this is the prelude, and this is the conclusion. Interesting. I don't know why it's pushing all of those when they're not used. Okay. All right, so we need to let's make this big again. We changed this to use x86 if. So we changed this one to use x86 if. We are getting errors where we did not modify the other parts of this program definition. So this has the number of stack vars and the used callee registers, right? But we are not. Oh, okay. So what we did that's different here is that we moved these there, right? So those are on the program now, not on the block, because the block is no longer a single function. So that should fix that problem. Oops, did I not move that to the right place? Oh, well, there's multiple ones here. Okay, so this one, and this one. Okay, so we should be able to run those tests, and they still pass. Now we need to come up with some tests for the changes that we made here. So what did we add? We added the possibility of comparing something with an immediate value. So we need to patch instructions comp immediate test. Okay. And then what are the other things we need to do? Patch instructions. We have move ZBQ into stack. And I think that's it. We can't really test this because it will panic, right? There's no. I don't think that there's any. We're gonna double check this. Gleam. Let's look at the documentation. Okay, language tour. So let's look at panic. Right, they're saying we shouldn't use it directly. There's, let assert, of course. There's no way to catch a panic. And yes, I agree. With well-designed types, the type system can typically be used to make these invalid states unrepresentable. Maybe we should do that. But in the meantime, let's just make tests for these. So, okay, we need something that does a comparison with an immediate value. And the thing is, it doesn't have to be a valid program. It doesn't have to be something that we would actually generate. We just want to test that this substitution occurs. So let's say the body of the block is sorry, I need these all prefaced with x86. Okay, we'll just assume that it's moved into there, and then we'll do RCX with an immediate of 5. Okay. We'll actually have set, which let's import equal. This is a dumb little program. Okay, so we're reading something from the standard input as an integer. We're comparing it with 5. Then if it's equal to 5, we return 1. Otherwise, we return 0. Okay, so that's our program. And what we want to test is that this gets moved into REX. Right? Okay, what's wrong there? Oh. Okay, got the parens wrong. Okay, so what I want to see is I'm going to copy these, and what I want to see is this gets replaced with right. So we've put the immediate value that's being compared into RAX, and then we do the comparison with the other argument unchanged. That's what the transformation is. Okay, so let's pipe that to patch instructions. So if we do let assert okay block body actual dict.get p.body start x86.block. Okay, so let's say body actual should equal body expected. Okay, so there's our first test. Okay, so this one is to do. So that one passed. That transformation worked as we expected. And let's do one for the move ZBQ. So let's say, let's do something similar to this. So let's copy this. We'll make use of this again, except that we want this into a deref of RSP -8. And then we're going to do like I just want to make this make a little bit of sense. This doesn't make sense, but I was like, well, this is a Boolean type, right? The result of set. So we would never have integers and Boolean mixed in our operations. So what's a Boolean operation I can do in this instruction set? It's XOR Q that we were using for something else in our code generation, but in this case, we're just going to use it here. Maybe okay, so then we need to adjust our body expected. So instead of moving into this, what we're going to see, REX, right? That's what our expected should be, because you can't put move ZBQ into anything but a register. Which I guess makes sense. Because that operation can happen completely in arithmetic lanes or whatever. Okay, so now we need to say, let's do just like we did above. Let's do this. Okay, so we got a failure. So this is, okay, so we expected, right, move REX into RCX, move 5 into REX, comp Q. Oh, the problem is I left in this extra stuff. I'm covering things that were in this test, and I don't actually want to. So what I'm going to do up here, let's like pretend that these were patched already. So everything up to the comp Q, I'm going to replace with the already patched versions. Then we're not covering that test because that won't match. Okay, so now it passed. Again, this transformation is here, right? Okay. So, I'm not going to do the optimization challenge. We could make this into a test, but excuse me. Maybe what we'll do is we'll take this program and do it as part of our main, and see what it emits. But that means, well, first of all, let's look at the generate prelude and conclusion, and let's see if we can change this to if. And I think that it's going to break things, right? So, yeah. Okay, so we're going to have some problems down here, and the problem is that we don't care about the start block. We actually have this on the program. And then the same here. So, and then main doesn't need to throw those in there. Conclusion doesn't need to add those. And then we need to update our pretty printing. So I think that let's add the missing patterns. I see. Actually, need to do it like this. So we'll accept this to be compq. Right. So and then we'll need to handle. We'll need to handle jump if differently. Yeah, so XOR Q is more like comp Q. Okay. So jump if. So if we have equal, we have, let's do, where did we do jump? Okay. So it'll be a string tree from. Yeah, let's do it like we did jump. Honestly, I hate to do a lot of repetition there, but maybe what we can do is pipe the case. Pipe the case. You'd never do that in Elixir. So this is jump equal. And real quickly, I want to look at x86 64 cheat sheet because I think it has the conditional jump. Yeah. So yeah, jump greater than, jump not less than or equal to. Oh, x86, you funny. Okay. So this is jump greater than, greater than or equals also 1. Jump less than, yep. Label. Okay. And then move ZBQ, we need to handle a little bit specially. Right, reg to text does that. So we need a byte reg to text. Nope. Where is that type? Is it not an x86 base? It is. Fun. Okay. Right, we're basically going to do this. And then we'll do that. Okay, and this is just AL, oh no, AH. Okay, and then it's just complaining that it's not used. So up here, we will do basically like what we did for all these. Copy this one since it's the closest. And this is byte reg to text. And this is, I need to add the extra ZBQ in there, okay? And then finally, set is going to be more like jump if, right? So I'm going to actually move those closer together because they have similar patterns. So we're going to basically do this. Okay, so we've got, this will be set E, set G, set GE. Let's make sure that that's correct. We're not using conditional moves. They don't actually talk about the set instruction in this, I don't think. Oh wait, here they are. Right, so, right, set E, set G, set GE. So just basically like the jump instructions. Okay, and then we want the argument has to be a byte register. So then we want byte reg to text of arg. String tree append. I'm sorry, I don't need append. I want, let's look at string tree in the documentation. Append tree. Okay, so now we should have all the pieces put together to round trip our program. So we need to rebuild this based on the diagram here, right? Okay, so we're going to basically undo all that, but we're going to add shrink as a pass. So shrink, uniqueify, remove complex operands, explicate control, select instructions, uncover live, build interference, allocate registers, patch instructions, generate prelude and conclusion. Okay. So now what I'd like to do is take this program that they, since we now have, right, elif is a program. So let's comment this one out. So this is going to be L.if, and primitive operation. Wait, hold on. Let me remember the abstract syntax. Okay, so we know there's going to be a condition. The branches here are L.int 42. Int makes an expression L.int 0. Okay, so what's the if here? What's the condition? The other thing that we should do here is we should type check. And I think that that's, let's see, expression, if, primitive. Yeah, okay, so we need a comparison prim. So prim, comp, and then two expressions. Okay, so that's our program. We have let's call type check program. Okay, so we're just asserting that it type checks, and then we're gonna put it through all the passes and print it out. So, oops, what did I do wrong? Oh, I need to fix the tests. Okay, so let's x86 if. Okay, and then this is going to have the same business. And we'll probably want to update these tests to do some more stuff. Oops. Okay, so this was what we generated for our program. If equals read int or read 1, then 42, else 0. So so we have a main. It is interestingly only pushing RBP and RSP, and subtracting 8. So and then it jumps to start. So there's a lot of stuff here that I don't know Why those need to be pushed? Because they're not being used in this program. Okay. And then start calls readInt, moves to REX into RCX. We got that right. Compares 1 to RCX. Jump if equal to block 1. Otherwise jump to block 2. And there's our, numbered differently. So block 1 moves 42 into REX and jumps to conclusion. Oops. Block 2 moves 0 into REX and jumps to conclusion. Excuse me. And then main, we already did main, and then conclusion realigns the stack, pops RBP, and returns. Like this is pretty damn good. Yeah, like that feels good. We're not doing anything really remarkable here, but let's really quickly run those tests with the adjusted types. Yeah, okay. So uncover live test doesn't use that. I don't know why we imported that. Let's just remove that unused import. And then we have no warnings. Okay, so let's look at generate prelude and conclusion test. The only thing that I think that we need to adjust here is this passed. We know that the number of variables is correct. Like it pushed the right amount of times, it put in the correct alignment. Let's look at the program to text. Mostly I want to cover the new instructions. Compares, compq, set, the jump instructions, and so forth. That said, let's go ahead and make a real quick commit. And then we'll add a test possibly for that. The other thing that we could do is just skip it. I'm not incredibly fussed about it. One thing that's nice about this is it shows going from this to generating the proper instructions, and even though we rearranged like how our types are structured, we kept the same logic, and so we still generated the same prelude and conclusion, even though we had a different data structure. So that's nice. Yeah, I feel pretty good about that. And we can honestly say that with the exception of the challenge, which we didn't do, but I think we should probably read through it so we can understand why I don't want to do it. But we finished chapter 4 today, so yay. So let's look at this. So they're talking about optimizing control flow, which we don't have any control flow optimization right now. So what do they mean? They mean there are a couple things: generating blocks that are not necessary. So the additional jumps means, you have code that basically doesn't need to exist. Honestly, if you think about a program like this if read an integer is equal to 1, return 42, otherwise 0, you only need a jump for one of these, right? Because this will be like, this will compile out to, what did we see? Gleam run. Right, this compiles out to jump if equal block 1, otherwise unconditionally jump to block 2. The thing is, you can inline block 2 right there, because if you're not jumping to the then there's no reason to jump, because you'll just fall through. Or the alternate way is you could negate that condition, go jump not equal to block 2, and then just fall through to the then. These have implications on probably on branch prediction and so forth that I don't understand, but we could inline either one of these blocks based on the combination of these two instructions. So what they're suggesting is that the explicate control that we built before is a bit too aggressive about creating blocks. It's like, if this might possibly be reused, then generate a block for it. But if it doesn't have to be, if it's not going to be reused, like if you don't have branches on branches, then you don't need to generate blocks for everything. So let's read what they say here. I'm not explaining it that well, but the algorithm for explicit control sometimes generates too many blocks. It creates blocks whenever a continuation might get used more than once. So that's like, the next section of instructions you want to proceed with is either the then block or the else block, right? So those are what we previously called continuations. If there's a possibility that one of them gets entered more than once, then you would want to generate a block for that, so that the other entry points for that section of code can jump to it, right? But if there's only one, then you don't need to jump at all, like we just discussed. Okay, so some continuation arguments maybe not be used at all. Like, you can also think about the case where a branch might be eliminated. Then you don't need to generate a block for it. Okay, so consider the case for the constant true in explicate pred, in which we discard the else continuation. The following program falls into this case, and it creates two unused blocks. So let y, if true, read, otherwise this other thing. Right, so it's saying you're creating so start y equals read, go to block 5, return plus y2. So you never even enter block 6 or block 7, right? This feels like a bit of a straw man. I don't think that we would reach this point, but here we are. Okay. So we discard the else continuation, so you shouldn't have had to generate the other blocks. Now let's look really quickly at ours, because I think that we handled that. So explicate pred. No, we did not. Let's look up here. Right, so we... Okay, that's explicate is sign. Let me look at tail. So if it's in tail position, we call explicate tail on if true and if false, but we don't check the condition. Yeah. Now this is in an assignment position. So if we look at assignment, the if, yeah, we treat both the true, we create a block for the continuation, which you would expect. That would be like block 5 here, right? And then we do explicate assign on the if true and if false branch. But again, we're not checking the condition. Then we do explicate predicate on those. So here we are probably creating blocks, right? But if this expression is the constant true or false, you can eliminate one of these steps, right? That's what they're saying here. Okay, how can we decide whether to create a basic block? Lazy evaluation can solve this conundrum by delaying the creation of basic block until the point in time at which we know that it will be used. So Racket supports lazy evaluation with the Racket promise package. There's an expression delay, which creates a promise in which the evaluation of the expressions is postponed. When force is applied to the promise for the first time, the expression, so this is basically like promises in any other language that has promises. The difference here is this is like like in JavaScript it'd be a new promise and then a function giving reject and you know, the success branch and the failure branch. These are like these promises don't have failures. They only have postponement. So then the thing is, force basically does a mutable operation. If the result doesn't exist yet, then it evaluates the set of expressions here. If it does exist, then it just returns the same result as the first time it was called. So the reason why I wanted to skip this is Gleam doesn't have that sort of thing. We would have to create it with some FFI. It's actually not so bad. For instance, with Erlang, we could do it with the process dictionary potentially. With JavaScript, we would do it with a promise. And then, you know, force would call resolve on the promise with the expressions. The other thing that this implies is something that's not true in Gleam either, which is that the blocks are using global mutable variables, and we don't have that in Gleam. So that's why we were threading it through everywhere, right? So there's not really a place where we can say, you know, delay this, and then at some later point, you know, mutate this thing that we're using elsewhere in the program. Like, that doesn't make sense in Gleam. Now, in a lot of cases, what you might do where you have this sort of mismatch between the language semantics and the design pattern you want to apply is that we could say that we would thread this through, but this actually would not if we wanted to create a block, oops, go back to chapter 4, please. That would be sort of like push an effect, a delayed effect, right? So it'd be like, hey, there's this intention to create a block, and we maybe give that an identifier, and then at the end of all of this, we would run through and evaluate all of the effects, right? So a delay might not necessarily generate a block that gets added to the program. We might just have some sort of thing that just records the operations that would be and then interprets them at the end. This is the sort of idea of what a lot of async runtimes do, is that you build up something that looks like imperative code, but it creates a type which can be interpreted by a runtime. And then that runtime will hook up the low level things like watching a file descriptor or polling the operating system, like those sorts of things for an async runtime. But it's the same sort of principle here, is that we would basically be creating a delay effect and then an interpreter for that effect. So I don't know that this... so then it's like this force, right? So our interpreter for these effects would look like a sequence of delays and then forces, and then we would have essentially our state of over interpreting all these effects be when we would keep track, like we do the accounting of what blocks had been created, and then when you call force, then it's like, oh, here's the value that was already there, or here's the name of that created block, right? But if you never force the thing, then we wouldn't inject it into the cached output. We could do something like that. I think it's a little bit complicated because we don't have global mutable state. Now we could also say, hey, this block cache is an opaque type, and then we will manage what that looks like in FFI. That's another way we could do it. Okay. Long-winded discussion for something we're not going to do. Okay. So it's saying if force is applied to an argument, it's not a promise. Force simply returns the argument, right? So use promise for the input and output of functions. So like they're basically saying these functions explicate, pred, assign, and tail will return promises both as the input. So like for the continuations here, this would be a promise of a tail, a promise of a tail, a promise of an expression possibly. No, you can't promise this expression, but you could promise the tail. So any place where there's a continuation, you would return a promise, and this would return a promise of a tail as well. And then you would call force on the top level promise. So the delayed computation that creates a basic block for each continuation, and then returns a go-to statement for that basic block. Okay. So they're saying create block for tail. Says defer, basically, delay. Set a variable t to the force of tail. Match t if it's goto, return goto, else generate a symbol, for the block. Add it to the basic blocks, and then goto label. Yeah, this is the part that, this is not possible in Gleam. Not in base Gleam. Like, we can add FFI to make it possible, but it's not. And this is mostly just adding this delay and define over the tail. Otherwise, it's match tail. If it's already go to, then you just go to. Otherwise, you generate a block for it. Okay, so 4.16, if you have the improved explicate control, you don't get the other blocks generated. Okay, the thing is, I want to say that, bless you, goodness. I want to say that we did the we did that optimization earlier in an earlier pass. Did we do that in shrink? No. Where did we eliminate? Did we do it in RCO? We might have done it in RCO. No. Okay, so it might be, where did we, so shrink pass? Was it the shrink pass? I distinctly remember doing this somewhere. Well, let's look at our phases. So it's got to be either here in one of these three. I don't think it's uniqueify. Let's look at uniqueify real quick. Yeah, we don't bother with that. All right, well, maybe I'm dreaming. Let's look one more time at remove complex operands. I want to say that we already handled this Boolean literal in the condition position. But I don't think that we did. Yeah, we're just translating ifs. Translating ifs. Right, and that's complaining we didn't run the shrink pass because and or are not possible at this, or not possible to handle at this phase. We translated it to ifs. Let's look at explicate control again. Yeah, I think we're not handling. Oh wait, hold on. No, here it is. The thing is, this explicate pred branches on the condition, which is an expression. And what we do here is if we have an atomic value, we already did this optimization. But we're not doing it lazily, right? If we have an atomic Boolean value here, we know which branch will be called. So we don't need to, we just return the if true branch or the if false branch based on the contents of that literal value, right? And then here we're inverting it. So I think we've already done this. Let's, for argument's sake, let's make this program. This will be the last thing we do today. Let's make this program, and we'll feed it to our main, right? We'll construct this in the elif language. We'll feed it to our main and see what comes out. It'll have the prelude and conclusion and so forth, but yeah, we can see whether this is generating unnecessary blocks. All right, let's make that happen. Okay. So let me get this where I can see both of them. So we have a program, and it's a let y and there's an if so this has bool true, and then it's going to do read, right? For the, and then there's going to be elif. This is the in the else branch of that let. Comp. Okay, so that's the condition. And here's the, excuse me. I'm sorry, my cat is licking my arm as I'm trying to do this. Okay, so, and then there's another let in here. X. And then we have add, or primitive operation. Add plus, sorry. At some point we will get a Luxor and parser for this. We just don't have it right now. Okay, so that's, and then we'll do plus, except this is an l.prim, right? Int 1 dot, oh, I'm sorry. This is l.var y l.int 2. Okay, so that's, what do we got wrong there? It's not. Okay, so this is, yep, that's it. We're we're missing some parens here. Okay, there we go. So there's our program. Let's see what it becomes. Okay, so we are generating unnecessary blocks here. Let's read through this. So start readInt, right? Move rex to rdx, and then it unconditionally jumps to block 1. Block 1 is add to rex, jump to conclusion. So we are still generating these extra blocks. So we didn't actually solve the problem via our little optimization there in explicate control, but I think the issue is that we generated them before we looked at the condition. So that's where I was saying, use lazy generation and so forth. So it's a good demonstration, I think. We may add example program for the block optimization discussion. We may try to address this later. I need to think about that before we jump right into it. But we can also just move on. We are generating dead code. That's the main problem. Now, if I were thinking about this from the perspective of a compiler architect and a user, I would be going, hey, this is all dead code, but at a much higher level. You could like do partial evaluation or in partial interpretation of the program and go, this code will never be called. You can eliminate that and say let y is read, right? This is the sort of things that language servers do, but we are not that sophisticated yet. So we would need to do the sort of lazy allocation of blocks. And then the second part of it is removing unconditional jumps. So if there's only one jump to block 1 after you've eliminated the ones that are dead code, right? Then you can inline block 1 into that jump. That's what this section is about. Yeah, so if there are no other jumps to block 5 in the rest of the program, so this is sort of like, you can think of the program as a graph again. We had that control flow graph. If you can show that there's only one edge into a block, then you can inline that block in the source of that edge. And we do have our control flow graph that we built. We had it with this Erlang FFI because it's got the nice digraph library. But you could potentially do this with JavaScript as well. And in fact, I had pulled up here. Maybe this is something we can do next time for fun. There's this graphlib. Let's see. Let's just look at the code. Yeah. So they have good documentation here. It has topological sort built in there, and we can do some of this stuff under the hood and keep it opaque in our FFI, just as we have for Erlang. But we would need to do additional externals there and so forth. So maybe we'll play with that next time. Anyway, if you're here, thank you for coming. Thank you for sitting through this, and hopefully next time we'll either do this additional FFI to JavaScript for fun, or we'll go on to Chapter 5. I haven't decided yet, but I hope to see you next time. Chapter 5 promises to be pretty exciting and intense, just as Chapter 4 was. And so we will look for you next week. Thanks so much.